So welcome to everyone. Very pleased to welcome you to this new edition of the networking channel. So today we are going to have a program which is dealing with the exploration of the future of the networks, or the future networks. We are very pleased to have with us three panelists live, and Aki Nakao from Japan is going to be through a video. And at a time when the community and various stakeholders are exploring the design beyond 5G and most particularly 6G and the research infrastructure that are supposed to support this design, we're very happy that today we will have an illustration of some interesting research platforms worldwide that are being deployed and that provide opportunities for international cooperation. So, without delay, I will start first by playing a video from Aki Nakao, who is going to provide us some information about how things are evolving in Japan. And then, of course, I will hand over to the other panelists. It's important to remind you that, of course, this program is recorded. It will be available on our YouTube channel. And also, in case you would like, of course, to ask questions to the panelists, you can use the Q&A. And we have also a Slack channel that will be advertised on the chat. So I will go now with the video of Aki Nakao, who will provide us with some very interesting information about international collaborations for beyond 5G and 6G.
My presentation title today is International Collaborations for Beyond 5G and 6G. The further upgrade of 5G features. And also we have ultra low power consumption, ultra security, resiliency, autonomy, scalability goals for adding new features contributing to generate sustainable and new values. So in order to promote these goals for beyond 5G, so we think that international cooperation is a very important factor here. So first of all, our Beyond 5G Promotion Consortium and the 6G flagship project at the University of Uru has signed the MOU in June 2021. So this was the first MOU of Beyond 5G Promotion Consortium with an international organization. And areas of cooperation was three things. The first, exchange of information and publications. Second, personal exchange. And third, the collaborative research and development projects. So in last May, so the Prime Minister Sanna Marin came from Finland, and we had a wonderful event, a Finland-Japan joint seminar for beyond 5G. And there she delivered a speech on cooperation with Japan in the 5G and 6G development. And we plan to exhibit the results at the Osaka Expo scheduled in 2025. And President Fuji presented the talk and also touched upon the importance of the Finland-Japan cooperation regarding the beyond 5G. And we had a great panel with distinguished experts there. And the panel conclusion was presented at the website of the University of Tokyo. And we identified very concrete goals and also joint research systems and also field experiments funding. So these are concrete steps forward that we identified in this panel. So this was announced in the 6U flagship website also. And we are seeking the concrete joint project right now. So not just the 6U flagship, but we have signed up for MOU with the 6U IA. And likewise, we have a bunch of goals for this MOU. And also with United States, we have MOU signed on May this year with Next Year Alliance led by the ATIS. And also we are right now working with Power Project in US. That was a great project. And we are also looking for another opportunity for MOU sign up for other organizations in the international arena. So recently we, so by the way, we have Beyond 5G Promotion Consortium structured like this. We have a general meeting, and under that, in this umbrella, we have a planning and a strategy committee and an international committee where I'm chairing. And recently, we created a new subcommittee called Open RAN Subcommittee. So as you may know, the open interface between the components consisting of beyond 5G and 5G telecommunication is very important. And this Open RAN activity was endorsed by the Quad Leaders Meeting, which was held in May this year. So, but now not just the 4 countries, but Open RAN activities has been extended to all over the world, and we all understand the open interface. This is very important to create a new ecosystem and include new stakeholders. So at the University of Tokyo, we started a new organization called Collaborative Research Organization for Next Generation Cyber Infrastructure, shortly, NGCI. So this NGCI is a virtual, sort of a virtual organization across the many schools within the University of Tokyo, engineering science, information science and technology, information technology center, and etc. And we have 12 organizations attacking the research goals of these, listed here. So this research area corresponds to the goal of KPIs that I just introduced in earlier this presentation. And it stands for EMBB, URLC, MMTC enhancement, low power, security, quantum mathematics, and autonomy flexibility, which means that softwarization and machine learning enable infrastructure, and the frontier communication like NTN and ocean underwater communication. And also we have to develop the applications using local 5G and beyond 5G technology that is listed above. And not just technology, but also we have to think about data governance and policy making and beyond 5G strategy. So these are the activities that we are pursuing in this NGCI organization. So we also started the dev showcase in my lab So we try to seek for industry academia collaboration, and we open the campus space for this activity. And we invite lots of companies, and we conduct joint research within this space. And also, we are using this space for PBL, project-based learning, for students. So using these type of tools, we have right now the 27 projects within the University of Tokyo. And if you go to the top page of the University of Tokyo, so then you can take a look at these details of each project and related to the Beyond 5G. So, it's called a Next Generation Satellite Infrastructure Initiative. And so if you are interested, you can go there and check out. So I can introduce some of the projects that I'm leading. So Nakao Lab is running a 6 national project related to Beyond 5G, and as well as 3 national projects related to post 5G. So the time frame is a little different for Beyond 5G and post 5G. And I don't have time to cover everything, but I can just introduce Beyond 5G national projects, Ka-band satellite communication, satellite ground integration, and IoT system on chip. So this is a semiconductor project and IoT solution construction platform. And number 4, so the research development of the CPS, cyber physical system computing platform. So this is integrating AI and machine learning into our infrastructure. And number 5, the research on the IoT ultra coverage using low Earth orbit satellite. So this is an interesting one. So I'm spending the next slide to explain a little bit more. And number 6, this is the application, MARS, the mobility as a service, smart urban transportation infrastructure using the Beyond 5G technologies. So if I have a chance, I'd like to elaborate more detail of these projects as projects go on. But let me just introduce this number 5, the IoT ultra coverage using low Earth orbit satellite. So this research is about the development aiming to construct the ground satellite network to enable direct communication between LEO, so low Earth orbit satellite, and using just the commercial regular smartphones, no modification to the current smartphones, and also NB-IoT L2 terminals, so that we can cover 100% of the national land area. So right now, Japan has only a 70% of the coverage of the national land area, although we have over 99% of coverage in the population area. But so we like to, don't want to modify the smartphone, and we can just use our regular phone, but satellite with a large array antenna can, accommodate the signals from the regular phones on the ground, so that we can do communication all over the national land area. So if you're interested, contact me. I can explain more in detail about this project. So we are very excited about this project. Okay, because of time constraint, I can just summarize my talk. So we think that R&D of Beyond 5G cannot be realized within a single country, and we have to maximize the opportunities for international cooperation of the next generation cyber infrastructure. So we need a concrete step forward joint project for international collaborations. We are right now discussing on this opportunity with several partners, especially the partners within this MOU that we signed up recently with the international organizations. So if you're interested in our activities, please contact me. We can extend our activity together. Thank you very much for your attention. This is another talk.
So thank you, Aki. We know it was difficult for you to join live because it's very late now in Tokyo, but we got the message that there are a lot of activities going on in Japan and that you are calling for more international cooperation. So for those who are interested, of course, we are happy that you will take the opportunity to contact Aki directly. And now I'm very happy that we can see some other fundamental research topics and how they are going to be addressed. Especially, I will hand over to Hongwei. He's going to discuss rural broadband with quite new power, the last power project that started about a year ago. So Hongwei, it is a pleasure that we have the opportunity to see how things are developing. Thank you.
Great. Thanks, Sergey, for the invitation and for this opportunity to share some of the latest news about the project. Let me share my screen here. So can you see the slide now? Okay, great. So good morning or good afternoon or good evening, depending on where you are. And thanks for this opportunity again to share an update about the ERA project. For colleagues who may have seen ERA discussion before, this will be a refresh of some of the latest development. And for colleagues who may be new to ERA, this will be hopefully provide a very short overview about what ERA is. Okay, so as Sergey mentioned, ERA is one of the latest. It's the latest power project in US. It has a unique focus on rural broadband. With attention to the technology aspect, look at what's actually beyond what has been talked about today, right? In terms of how to address the rural broadband gap we have today. One of the, besides looking at the fundamental research, applied research, one objective for this effort will be to actually look at technologies that can potentially reduce the cost of rural broadband by a factor of 10 or more. That's essentially what's going to take in US, at least, to make rural broadband as affordable as urban broadband. So as we examine the technologies and use cases, we would also pay special attention to the need of rural industries, such as precision agriculture and so on. Now, to this end, the deployment of ERA will be something like this. So we are deploying the basic high-throughput, long-distance wireless backhaul solutions in central Iowa, spanning quite a few cities shown here, covering an area of diameter about 30 miles in diameter, involving up to six cities, rural cities, and also some the agriculture farms. At each site you see here, there will be also advanced access network that's going to be deployed. And then in the center state of Ames, this is where we would see a little bit denser deployment at base stations at the research park, Curtis Farm, that's one of the crop farms here. And then there, besides research farms, we do have a producer farm and also the US Farm Progress Shield Center that's going to be within the coverage range of the ERA testbed. So that's at a high level what the topology and the spatial distribution of the sites will be. Just a little deeper, a little bit on the details of the technologies that will be featured here. Regarding the long-distance high-capacity wireless backhaul, this is where we would be deploying. We're actually deploying the technologies that would operate at a wide spectrum of a frequency band from the 194 terahertz free space optical link to microwave and microwave links. We're also looking to the possibility of deploying some new SATCOM user terminals so that you can experiment with the new SATCOM in mind. So just want to highlight one new platform that's been developed right now as part of the project. That's the free space optical, the ERA optical platform we're developing that can potentially enable up to 160 GPS capacity at a distance up to about 15 kilometers. So the testbed will be developed in a way so that researchers can actually experiment with the individual platforms, but can also leverage this diversity to try out solutions that can improve the robustness of high capacity wireless NICs. Because that's actually one of the gaps today. There have been use of wireless backhaul in the literature in practice, but the level of robustness that's available to the the production systems for end users is not as satisfactory as one would like to. So that's about the backhaul. And then on the access network side, this is where we would see both cards and also fully programmable SDR systems being deployed. This include cards, Ericsson 5G, massive MIMO, and millimeter-wave radios, as well as NI SDRs plus the low UHF massive MIMO platform from Skylark. Skylark platform is actually quite unique in the sense that it's going to be multi-antenna systems at very low frequency band. It's going to have a commercial grade implementation that's available for researchers, but also you can also treat this as a fully programmable SDR platform. So with the access network, we would be able to enable research in basically all dimensions of 5G type of technology, but in a specific rural settings, and also different kind of geographic and environment settings in the aerial system. So besides access network research, there will be edge computing resources that's embedded into the different sites so that you can run integrated access network backhaul and also edge compute experimentations. Just one slide about the coverage. So essentially, we expect to be able to cover anywhere within about 6 miles range, 6 miles radius from the base station sites. That essentially means up to quite a few hundred square miles of area will be covered in central Iowa. So therefore, for the aerial project, besides support fundamental research, one of the objectives would be to enable real-world application trials. For example, agriculture is actually one of the main focus, so that as we deploy the user equipment radios, we would be able to actually make sure that we cover a diverse set of settings for agriculture, including crop farms, livestock farms, also the farm facilities, including like green mill, biorefinery, and so on. And then some other user equipment that will be adopted here or connected, including some of the bigger like John Deere ag vehicles, some robots, also potentially some drones, and also cameras, sensors, and then in livestock farms, there will be also cameras and so on. There will be actually a environmental sensor and control facility that will be connected, so that can be ready for experimentation, and also there will be potentially one solar farm that's going to be connected. So there will also be, besides the agricultural farm deployment, there will be user equipment radio deployment in the communities, for example, fire commando vehicles, fire trucks, and also potentially the airport within the footprint of ERA. So building around upon the power investment, we're also going to add, probably starting in the coming months, also adding some additional elements to the testbed so that you can actually run experiment with US control channels, for example, CNPC channels and payload channels related. You can run experiment with those and also try out potential spectrum, dynamic spectrum allocation strategies. So that's a high-level overview about ERA power testbed, also the extension to the National Radio Dynamic Zone effort. So where are we today? So we're actually in the process of completing the phase 1 deployment that involves 4 base station sites around the state of Ames and ISU, right? Touches on the Wilson Hall, Curtis Farm, Research Park, and the Agronomy Farm. Once this is done, essentially about the this whole state of Ames and the surrounding farms will be connected. So here are just some footages about the photo. So the deployment is expected to actually complete by Friday next week. So we will also be working on, once that's done, we will be working on the user equipment radio deployment around the farms and communities and so on. Besides the access network, there will also be one backhaul link that involves one free space optical link, millimeter wave and microwave link that will also be made available as part of the deployment. As I mentioned, the deployment we will complete in the coming weeks. We will be doing a lot of testing in the coming month. And if everything goes well, we will start actually beta testing in November, in about 2 months from today. We're actually looking for volunteers who may want to be the first group of colleagues in the community who want to try out the testbed. If any of you would be interested, we would very much love to work with you to kind of test things and before we open this to the public. Basically kind of troubleshoot, right? Make sure that things are working well. We also have a Google group that colleagues can sign up. This is where we would actually communicate with the community about news or any features or any other interactions or events. Or if you may have other questions, you can feel free to contact us at contact@aerowise.org. Okay, so that's a brief summary and update. Back to you, Suki.
Thank you so much, Hongwei. It's interesting because we have seen from the presentation of Aki the importance of fundamental research topics, but also where they will eventually meet industrial needs. And in your case, of course, we see how enhancements in the technology should support new verticals. So we will discuss certainly this later. And I'm very happy now to give the floor to Raymond. So from Japan to the US and now back to Europe.
Okay, I was a bit startled there, Serge. So let me share my screen.
Yeah.
Oops, that's the wrong one. I'm sorry.
So in the meantime, if the audience would like to ask questions, you can use the Q&A. And of course, we'll be happy to take some questions live after the presentation.
Okay, so Serge, I hope, is this okay?
Yeah, if you can go to full screen mode, that would be better.
It says it's paused. It says my screen sharing is paused. I've never seen that before.
You have to restart your presentation, I guess.
Let me stop sharing.
Yeah.
Okay, is this okay? Now I put it on.
Yes, it's not in the presentation mode yet.
Yeah, it's because there's too many things on my screen here. Okay, I hope that's okay now. Is it presentation?
That's perfect. You go
okay.
ahead. Thank you.
So thank you for having me. I'll try and be efficient here. I'd like to talk a little bit about the way we are envisaging what I'd like to call post-5G experimentation. So just who am I? My name is Raymond Knopp, so I'm Department Head of Communication Systems at EURECOM. I'm also the president of the Open Air Interface Software Alliance, which develops tools for experimentation in 5G and soon post-5G networks. So EURECOM is a research center in the southeast of France on the Côte d'Azur near famous places like Nice and Cannes. But we also do science on the Côte d'Azur. So, you know, what do I mean by post-5G experimentation? You know, when we're on our road to 6G, which is going to take a few years, the first thing that's necessary really is to actually evolve beyond 5G using 5G technologies. And I think we heard this in the previous talks too. But you know, from our perspective and in a lot of the work that we're doing together with some of the people here, we're looking at large-scale end-to-end platforms. So building, using 5G technologies, large-scale platforms. By that, I mean multi-cell site and also multi-region that make use of common infrastructure blueprints across sites. So we're reusing a lot of the technologies in multiple sites so that the communities can collaborate on the basic technologies themselves and replicate experiments, or what we can call reproduce experiments, through reusing and collaborating on tools. And tools are both hardware and software tools. To a very large extent, this is in line with the objectives of the Smart Networks and Services program in Europe, in particular streams C and D. And it's also, which is really a joint academic and, or industry and academic, I would put industry first when I describe that, in the European Union. There's another initiative that Serge is running on behalf of the European Union called the FutureG Research Infrastructure, which has similar goals, going beyond just telecommunications, but has similar goals of doing reproducible experimentation on a large scale in Europe and providing sites where people can do experimentation. So these are two big initiatives now in Europe where people are building platforms to do large scale end-to-end work. And, you know, from the perspective, what we're doing at EURECOM is really trying to focus on technologies that target the integration of disaggregated 5G radio access network and core networks with cloud native deployment frameworks. So that's stuff that we've been doing for the last few years, and now we want to bring it out and deploy it on a much larger scale, and to experiment with fine-grained automatic control of network functions. And this is actually something in line with what people working in the O-RAN ecosystem are pushing. So we are actually trying to experiment with concepts in using O-RAN architecture and actually pushing back ideas into the O-RAN ecosystem. And actually also really try and integrate new applications on experimental 5G infrastructure. So that's something that's happening a lot in these SNS projects, looking at new vertical industries on top of the infrastructure. So to give you an example, this is a picture of the site that we're building in Sofia Antipolis, which is called the Sofia node. Basically, you can see here the buildings on the right-hand side. That's the EURECOM building. On the left-hand side is the INRIA building. We have interconnected these buildings with the high-speed optical interconnections so that we can connect our two computing and radio infrastructures together to build a fairly large site. This is actually only one cell site per se, although we do have indoor and outdoor components. You can see one of the outdoor components on our building, and this is an anechoic chamber inside of INRIA. These are all interconnected, and we can build fairly complex 5G experiments in this infrastructure. But we'd actually like to branch out now and have multiple sites in our region. And you can see here up on the top to connect to other networks in Europe, using similar technologies to have really a fairly large-scale experimental playground for emerging technologies. You know, at a very high level, the site really combines radio resources with high-speed computing resources and programmable network resources. And all of this using various open source software and automation tools coming from Open Air Interface, because that's something very close to us, but also using tools from the Open Networking Foundation like Ether or SD-RAN. Of course, using other frameworks for deployment like Kubernetes or OpenShift. And also continuous integration, continuous deployment frameworks to be able to develop software using the site. If we look a little bit further how this is interconnected, it will be interconnected to other sites. For instance, the site that Serge is building in Sorbonne will be interconnected to our site, and we should be able to do experiments with sites in Paris, but also with sites in other parts of Europe. These are things that started also in the previous framework project in Europe, in the ICT 17 and 19 projects, where you had multi-site experimentation. The spirit was a little bit different. They weren't so tightly interconnected, except in a few cases. But I think we're going to see more of this in the 6G smart networks and services in Europe. And we'll also have interconnections maybe with more industry-driven initiatives. I've put one here in a picture of the Engage 5G initiative in France. This is really industry-driven. where we use some of the infrastructure like the one we have in Sophia Antipolis with equivalent or complementary technologies in some of our industry partners. But this becomes a very complicated network of academic and industrial research labs that are trying to do end-to-end large-scale experimentation. As a very high-level view of the site in Sophia Antipolis, what you can see, and this is really from the perspective of a vertical surface integration perspective. Really, in the middle here, what you see are a series of clusters. So these are Kubernetes clusters. Some of them OpenShift clusters. Some of them are real time. Some of them are very standard IT cluster technology, combined with high performance switching and radio equipment. And around the end, there are tools for doing network orchestration, cluster management, and end-to-end service orchestration. That could be local, but that could also be from a remote site. And on top, what you can see is really what we're proposing for users of the site, from usually industrial users, to actually build use cases on the site, develop the software, deploy the software, and test the software using a CI/CD toolchain. So that's one particular site that's being built in the EU framework. Now, if we look at what kind of experimentation we would do in the post-5G era, really we have to look at some of the services. So typically we're interested in looking at studying cyber-physical systems, both stationary and vehicular, where we're going to be pushing for shorter range links with very low latency services. Just to give you an idea, today in 5G with sub 6 gigahertz access, we're talking about 1 to 2 milliseconds one-way latency with the devices that you could buy off the shelf today. We have to push that down to like 100 microseconds one-way latency if we want to start going towards 6G. We'll be talking about merging of sensing and communications in the air interface. There will be more device-to-device or advanced relaying topologies, both for private services or public safety and military. And this is really in line with the work that's being done in the 3GPP in really 17 and 18 sidelink and extensions of the integrated access and backhaul. This is a big area. And all of this will lead to what you can call network control systems, where you have intelligent wireless networks that are controlling devices moving around in the network. In addition, we would consider also advanced IoT use cases, both low rate for metering and very high rate video sensors with 5G RAN, to go beyond what we're doing today in systems like LTE-M and NB-IoT. And finally, for IoT, in my opinion, what we're doing a lot at EURECOM are looking at paradigms related to time-sensitive networking, both for Industry 4.0 applications, but also for real-time multimedia, and looking at these combined communications and sensing control paradigms. Also, not so much in our area, but in other labs doing similar things, the non-terrestrial networks are gaining a lot of interest in the post-5G experimentation. Now, in parallel to this, we look at integration of 6G technologies on the fly. So we will have these large-scale infrastructures for experimentation. We want to start putting in some new technologies as the ITU and 3GPP start specifying requirements and architectures. So we're talking about things like reconfigurable surfaces, the combined communications and sensing I mentioned before. Of course, higher frequencies, also high, just slightly higher, like 6 to 8 gigahertz. That's a lot of that has been talked about recently. Millimeter wave, of course, there are many sites that are already doing that, but there's more work to be done there. And terahertz communication. Some of the sites now are also looking at optical wireless communications, so visible light or infrared, combined with 3GPP air interface technologies. So that's the key thing to start looking at, the combination of optics and radio in a common air interface. All of this is in line with the streams A and B of the European Union Smart Networks and Services joint undertaking. So, and this will happen in the time span starting in 2023 to 2026 to make these technologies ready for 3GPP standardization, which will occur starting already 2024, 2025. If I can just quickly say a little bit what we're going to need in terms of spectrum to do this sort of thing. Today in our sites, both indoor and outdoor, we use 2.6 gigahertz on 40 megahertz channels for both indoor and outdoor. Also 26 gigahertz for short range indoor testing. But this is basically for one experimental cell around our institute. If we want to get to the point where we're doing multi-site experimentation, we're going to need more spectrum than that. That's not enough. So some of the sites are asking now for usage in above 3.8 gigahertz for broadband. So looking at more than 40 megahertz channels, 100 megahertz, 200 megahertz channels for advanced experimentation in the European Union. Also, academic research infrastructure like the Slices initiative I mentioned before, or the SNS projects will need this in the coming few years. If we have this, we have the possibility to deploy multiple experimental sites in a given region and in multiple regions with a common radio technology. And this will really target O-RAN experimentation using O-RAN radio units and also the development of the applications of O-RAN, so the famous XApps. And this will allow us also to do experimentation for distributed network functions over large geographic distances. That's the only way we're going to be able to demonstrate some of the challenges in disaggregated radio access network and core network technologies. I think we will migrate to 6 to 8 gigahertz for the 6G projects in Europe fairly quickly, both for indoor and short range outdoor. This was already discussed in some of the Stream V proposals that we were involved in. Higher frequencies are clearly going to be interesting, millimeter wave and terahertz, but I think for large scale experimentation, this is not going to happen very easily because the components are still very, very expensive and we can't replicate huge amounts of millimeter wave or terahertz communications equipment. So we will probably be limited to lower frequencies for large scale experimentation. And then, of course, start integrating the VLC and infrared during the 6G experimentation phase as a carrier in addition to radio. So I'm going to stop there and maybe answer questions on the fly.
Thank you so much, Raymond. It's very nice to see that on the one hand, you shed light on the concern related to end-to-end experimentation at a larger scale, and especially using open source telecommunication software. And on the other hand, of course, it is important that we can get access to specific spectrum bands in order to develop some original experimentation. So I will now switch to Rudra, who is going to provide us with some presentation related to the EURECOM project, which is one of the power projects, the third one.
Okay, thank you, Serge, and the networking channel, and it's very good to be able to present here, so I appreciate the ability to do so. And I hope the slide is visible and I'm audible. If otherwise, please let me know. So I've tried to prepare something that's in the nature of an update, because certainly some of the folks present here may have already heard EURECOM presentations, but also to give a very brief overview as part of the same update, so that whoever is not previously familiar with EURECOM may also get a sense of that. As a result, I have lots of slides, and I'll be going through some of them at lightning speed. Apologies in advance for that. Much of this information is also on the EURECOM website, which is linked from this title slide, as you can see. And you can also contact us on that email address provided. And having said that, the very first thing I should say is that it's a fairly large team that executes this project and is working on this testbed or facility, obviously. So I won't go into that with more detail. Once again, details are on our website. NC State University, where I'm at, is the lead partner in EURECOM. And that's where the bulk of the testbed is as well. As Serge has said, that this is also another of those power testbeds. We were the third one to be funded. We started in late 2019, September 2019, our project was awarded, and our phase 1 was scheduled to begin. It began in February of 2020. So right off the gate, we were hit with the pandemic, and that changed a lot of our timelines and plans, but we have been going at basically the same thing that we intended from the beginning, which is that just like the Platforms for Advanced Wireless Research program says, it's really about creating a testbed accessible by a nationwide community of researchers for advanced wireless experimentation. But for us, it was also about drones or unmanned aerial systems, which are, as far as, from our point of view, they have a synergy with wireless research. They're very useful in doing wireless research. Wireless research is motivated in turn by the requirements of drones, and there indeed are potentially mobile wireless joint research programs, research problems in wireless, 4G, 5G, 6G, next G kind of wireless, as well as other kinds of wireless communications together with unmanned aerial systems. So we wanted to have something that would be a programmable radios, which would allow you to do experimentation with wireless at any layer, including down to waveform design, if that's what you want to research. And also on programmable drones, which would create programmable mobility in a 3D airspace, repeatability, which is so important for science, and dependable results of research, and do it all on a programmable facility, which can be so that resource allocations and partitions can be very easily accommodated. This is an attempt at capturing in one kind of picture all the various kinds of research that potentially can be fueled by this kind of programmable radios on programmable drones on a programmable network. And I won't go through the details of this. Here's a quick view of where we are. Just for a quick reference, on this left-hand side, the map that we see, the north-south extent of that is roughly 5 miles. And the two yellow boxes show the footprint of the testbed by the end of this calendar year, which will coincide with the end of our phase 2. And what we have in that space are fixed nodes, as well as portable nodes that we can fly during, in that area. And the right insert calls out in orange the area that we are able to fly over now, which will increase to the larger area shown on the left in the coming year. Passing quickly over these next few things, we have fixed wireless nodes that are made out of commodity computers, software-defined radios, 4 of them on each of these computers of various kinds, our specific front ends, and so on. And we also have other fixed nodes, which are commercial equipment. We have an Ericsson system. We also have Keysight RF sensors. LoRa gateways are coming. They're not in the testbed yet, but will be by the end of this year. Facebook telegraph radios, which are already on there. And the goal is to try and put these up in the same places. For example, in this tower, this one shows the Lake Wheeler Road facility, which is an agricultural field laboratory where our first node has been operating. The testbed has been open since last November, and we have been supporting experiments by experimenters on this node and other portable nodes, and also there are nodes on the Sentinel campus. At this time, or as of a few months ago, we have towers and enclosures up for 3 other nodes in that larger space. The actual nodes are, still being connected up and will be operationalized. We are continually getting hit with supply chain issues, and we just found out that the computer enclosures will not come in until a little later than we thought. We're still hoping to do this by the end of the year. We will see. Portable nodes, come with both vehicles, which are specific custom vehicles fabricated with over-the-shelf and off-the-shelf components by AirPaw. So they are custom UASs, and the reason they're custom is that we want them to dovetail with our AirPaw portable node, which is a programmable node made out of an Intel NUC, most of them. Some of them are made out of smaller single form factor computers as well. So we can, and we have a smaller version of the drone as well. The same portable node can be mounted also on a ground vehicle, a ground robot, if you will, a rover, also of our own design. And that means that we can have not just controllable, but repeatable mobility patterns through the field of interest. The third key component is a good bit of virtualization equipment, a lot of backend computing, including some special purpose that is not virtual computing, but also hardware-based emulation platforms for wireless equipment, which enables very close simulation or emulation of the wireless environment out in the field, but in a controlled environment that allows a sandbox to be created for experimenters. So this requires a lot of FCC licenses, and we indeed have one of the innovation zones that have been granted from the Federal Communications Commission of the US as well. And simultaneously, it requires FAA, Federal Aviation Authority exemptions. For every type of new drone designed, these exemptions have to be reobtained. So we have done that for some of the stuff and are continuing to do for rest of the stuff. And as we have new vehicle designs, we will continue to recertify. The AirPaw team has components or people in it who have this expertise. This brings up the interesting question of how does one operate such a test bed, because it's a physical facility. It's not really fundamentally a computing facility. There are safety and regulations involved, and we have to stay within those laws and demonstrate compliance with FCC and FAA rules. We also want to operate commercial equipment, but do so on the basis of experimenters. But commercial equipment like Ericsson base stations are not built for that sort of delegated control. And yet we do want to farm it out to experimenters and do that as deeply as possible. Clearly not as deeply perhaps as a Linux computer is possible. On a Linux computer, we want you to have root access. How does one fulfill all of these sort of contradictory goals? And one of the answers is that AirPaw is a batch mode facility, which is to say that experimenters do log in live and program their experiment live, but they do that entirely on a virtual environment. And then we do not, however, try to go and repeat that experiment for them on the testbed. We actually shift their computational environment to the testbed equipment, the testbed computers, which would then execute their code exactly in a similar. So we use containerization technology for this purpose. However, these containers also have parallel containers that are control virtual containers, if you will, that monitor the experiments continually. And therefore, if there is any risk that an experiment might be about to violate or may have just violated some airspace or frequency space regulations, then we would be able to abort that. And this captures in a one slide the life cycle of the AirPaw experiment, starting from direct virtual design by the experimenter, and then return to that virtual mode of the results of the actual testbed execution of that experiment. I suspect I'm very close to time, if not, entirely over. So what I'm going to do is simply show a couple of things, pictures to leave you with. So this particular one was taken during an experiment. What that enabled us to do was to gather data like this, and the color coding indicates, spectrum, in a particular spectrum, the signal strength received. And the point is that nobody was standing there flying this aircraft. The aircraft was flying itself according to experimenter designed trajectories. And moreover, we can rerun this experiment. And as many times as we rerun this, we know that we are going over the exact same places with the exact same trajectory. This creates a lot of rich data, some of which we have published. Some of these are done by us ourselves, some of these by people we are hosting. One of the things I intended to show, I'm short of time, so I want the link is available on YouTube, where there was a recent kind of one-of-a-kind experiment that we attempted to actually take some of our drones, but be able to equip it with a camera and some backend cloud image and video recognition or analysis software that enables counting of cows, which seems frivolous, but that's the first step to then being able to monitor for sick cows and or pre-diseased cows and so on. But the interesting thing is that this is run through an Ericsson 5G base station, which is completely unmodified. It's the commercial stuff. With that, I'll just go over some of this other similar looking things that we had and finish my presentation. Thank you.
Thank you so much, Rudra. It's a very nice update about what you guys are doing, and of course we see obviously that it's a very challenging environment for experimentation, so we are really looking forward, and thanks also for the pointers. If we want to see more, then I guess that we can just visit the website. We just have time for maybe 1 or 2 questions. If the audience would like to ask questions, they can use the Q&A. There is one that I'm not sure whether there is an answer, but if one of you would like to address, which simulation tool is most efficient and agile till now for Open RAN according to your experience? I don't know if one of you would like to take this one.
Serge, did you say simulation tool? Or
yes, simulation tool, Raymond. If you can, yeah. If you can't, I guess that's maybe for you, this one.
Well, I mean, if I don't have a complete answer to that question, because most of the tools that exist for Open RAN, when it comes to the strictly speaking ORAN, are commercial tools. So I mean, there are tools from Viavi, there are tools from Keysight and a few others, but these are very expensive interoperability testing tools. We do have access to one of them, or we will have access to one of them, and I could give some more information once we do. But I think there's not really much out there. What is out there though are tools to actually deploy Open RAN components. So you'll find pieces from ONF, you'll find pieces from Open Air Interface, which you can put together to build at least prototype Open RAN equipment. I wouldn't call that simulation though.
Yeah, that's why I said I was not sure whether there is an answer to that question. Anyway, I don't see the question. No, neither in the Q&A nor in the chat. And I see that it's on the hour sharp now. So I would like to take the opportunity again to thank all the panelists, Hongwei, Rudra, Raymond, and Aki, who could not join, but to send us this video. And again, you know that the program has been recorded, so you will be able to see it offline if you will, and if you wish. And it is my pleasure to announce what we're going to have in 2 weeks from now. So we didn't speak much about security, and we would like to have this panel dealing with wireless security networking. So I would welcome you to join us in 2 weeks from now, same time. And in the meantime, we wish you a very nice day, a nice evening, and see you again in 2 weeks. Bye-bye.
Bye. Thanks.